Hi everyone! Previously, we have discussed the divisibility. And clearly, given an arbitrary pair of integers a and b, the divisibility is not always available. So how can we handle this general scenario? Well, to motivate our discussion, imagine that we want to measure a ribbon of 20 centimeters using a ruler of 6 centimeters. How can we achieve that? We can start by placing the ruler at the left end of the ribbon. That covers 6 centimeters, and it remains 14. We then slide the ruler to the right-hand side, end to end, for a second copy. That covers together 12 centimeters, and it remains 8. We keep going for the third copy. Now we have covered 18 centimeters, and it remains 2 centimeters. Notice that for the first time, what remains is strictly shorter than the length of the ruler. So we stop there, and the above discussion translates naturally into the mathematical equality. 20 is equal to 6 times 3 plus 2. This is precisely the division algorithm, which is so fundamental in elementary number theory, and it has many applications. Now, let us first take a look at the statement of the theory. The division algorithm actually states that for an arbitrary integer a and an arbitrary positive natural number b, there exists a unique pair of integers q and r where r is greater than or equal to 0 and is strictly less than b, such that a is equal to b times q plus r. Here, the letter q stands for the quotient, and the letter r stands for the remainder. To develop some feeling, let's first look at some examples. 20 is equal to 6 times 3 plus 2. Negative 8 is equal to 3 times negative 3 plus 1. 5 is equal to 8 times 0 plus 5. And 0 is equal to 2 times 0 plus 0. Note that the equality in the division algorithm should be considered as a map, where the input are a and b, while the output are q and r. Each time you gave me a pair of a and b first, I will be able to return you a pair of q and r in a unique way. That is the division algorithm. For instance, you gave me 20 and 6. I return you 3 and 2. You gave me negative 8 and 3. I return you negative 3 and 1. Note that we barely ask anything for q apart from it being an integer. But for r, we do have a very strict constraint that it must satisfy. The value of r should always be non-negative, and it should be strictly less than b. Otherwise, there will be more than one choice for q and r given the same value of a and b to make this equality hold. For instance, let a be 15 and b be 3. Then all the following three qualities are clearly true. But among them, only the second is what the division algorithm reads. The first one fails, as the remainder r is negative. The third one fails as well, as the remainder r is equal to the divisor b. Both are equal to 3, which is forbidden by the division algorithm. Another remark we want to give is that observe when r vanishes, the equality becomes a is equal to b times q. In other words, we're back to the divisibility. For this reason, the divisibility can be seen as a special case of the division algorithm where the remainder vanishes. Indeed, in absence of the divisibility, the division algorithm is often the best thing that you can have. Because no matter what are the values of a and b, once the division algorithm is applied, the value of r has only finitely many possibilities. This often provides us with an approach of proving a statement by cases, which is otherwise probably not available. Alright, now you have seen the basic concept of the division algorithm together with some elementary examples. In the next section, we will discuss the proof of the division algorithm.